Good afternoon, everyone. Thanks for tuning in to the Arbor presentation. I will begin with about 20 to 30 minutes introduction to Arbor. I will show what we've been up to recently and what we're about to do. And then there will be a demonstration on the eBrains lab, for which I hope we can all log in at some point during this meeting. For me, it's going very slow, so in case you haven't opened your browser to lab.ebrains.eu, you might want to get that started in the meantime. I have no idea how long that will take. It's taking for me now 5 minutes already, still not in. So maybe I should drop the link. I, of course, assume everyone has credentials for the eBrains lab. Please connect up, and then later we'll turn to it. Okay. Okay, still people popping in. Excuse me. I am have a slight cold, so my voice and nose are sometimes interrupting my speech. Apologies in advance. So my name is Brent Huisman, and I'll, like I said, will explain a little bit about Arbor in this presentation. So what is Arbor? Arbor is a library for writing performance simulations on networks of multi-compartment neuron models. That means you can use it to simulate large networks of morphologically detailed spiky neurons. What's, I guess, special for a simulator in this area, the area of morphologically detailed neurons, is that it's a pretty recent package made for HPC and GPUs from the start. So that means GPU and HPC support is built in for anything Arbor supports, any feature Arbor provides for you. So as you will see later, it will make no difference for your experiment whether or not you use any of those accelerators or environments, or you're just running on your own desktop or laptop machine, CPU. Now, we think, and hopefully you'll confirm this later, we have a very friendly interface and documentation. And another key design consideration in how you use Arbor is that we let you, or even force you, I should say, to separate the neuroscience from the execution. So while you design your experiment, you do not need to be concerned with how or where it's going to be executed. That can be defined entirely separate from the description of your experiment. And that way you don't design your experiment around hardware limitations or particular configurations, but you can use the same experiment and run it, for instance, first on your local machine, and then later scale up to some HPC system without changing the description of your scientific experiment. Then Arbor is developed out in the open. We have our source code on GitHub. We communicate through Gitter. Everybody can see what we're up to and can participate. So Arbor is a pretty recent project. That means our code is modern, and what that means is if you have followed any C++ courses recently during your education, you will feel right at home. Arbor is also a library, and that means it's easy to coerce into any workflow you might already have or want to design. We don't have a framework in which you fit your experiment. No, you can write your own and fit Arbor into whatever you find most comfortable or useful. Then a few projects that we have around Arbor. That's first off the GUI. Pictures are always nice, especially when exploring complex morphologies. it can be very, very helpful to see what you're talking about, where you're assigning a particular stimuli probes, but also parameters or dynamics. So here on the right, you see different kinds of regions for which you can write expressions. So you can describe and refer to them later. They are colored differently. And yeah, the GUI delivers visual interactive feedback on Arbor. Arbor runs as part of the program, so you are seeing what Arbor is seeing. There's no translation of anything. No, you look directly at the data that Arbor has in this process as well. So like I said, you can edit those, for instance, expressions describing regions or positions, and run short simulations, of which there's a small demonstration in the left bottom. Yeah, so that's something that's built with Arbor, and then something that's built for Arbor is it's still being worked on, but our NeuroML compiler is coming into shape. It's a project that is focused on converting NeuroML descriptions of experiments into Arbor inputs. So NeuroML is a language which lets you define neuroscientific experiments, and it's nice because it's a language that's not tied to any particular simulator. Unlike, so if you have worked in this field, then you are no doubt familiar with Neuron. It has its own inputs that are intimately tied to Neuron itself. That is not great if you want to store and transfer your experiments over large distances or timescales, because there's no guarantee such a description might work in 10 years or even longer. That's entirely dependent on developments in Neuron, and an independent specified file format like NeuroML is a way to separate those concerns and to have a description that will hopefully stand the test of time and makes it easier to collaborate. And yeah, it is not tied to particulars of any simulator. Yeah, I guess I described most of the first section here. Now, yeah, so NeuroML is, as far as we've seen, the most successful or advanced attempt at such an independent file format, and therefore we would like to support it. Of course, that means we need to be able to read those file formats, and that's where NMLCC comes in. It will take, well, it's already close to that, but the idea is that you can take a NeuroML description of a simulation, which can include cells, it can therefore morphologies, protocols, and then populations, and spit out an Arbor simulation that you can run as is. Yeah, so that's ongoing and very well advanced. We're using it to, we're using a, what's it called again? We're using an existing big model to test this and to make sure that works. Okay, who is Arbor? Like I said, we are developed in the open, so it's not just the core development team that is making up the code that's Arbor. But the core development team is located both in the Swiss National Supercomputing Center and the Jülich Supercomputing Center. And yeah, my colleagues are Ben, Fabian, Simon, and Lucas from Switzerland, and Anna, Leonard, and Thorsten, and myself from Jülich, working at Jülich. We also pride ourselves on code quality, so nothing enters Arbor without review. We have unit tests for much of our code, and we have continuous integration set up. So we try to be a well-behaved software package, in addition to being a good and fast simulator. Then the status, our latest release is 0.7. So usage is always a bit tricky because Arbor is a fairly new project, so I think most of our users are exploring using it for a study and not necessarily actually doing research or ready to publish research done with Arbor yet. But in terms of GitHub forks and stars, we are doing not so bad, I think. We have about 1,500 commits now in total making up Arbor, and quite a few lines of codes. And yeah, contributions have come in total from 29 people, as far as I could determine, from at least 10 institutions. So it's not only an in-house thing. There are actual people from all over, mostly Europe, I think, that are investigating Arbor and trying to use it to do some science. Then we have a release cycle. So every 3 months, we try to push a new release out. I didn't update the date here. We're a bit late on the 24 October release, as you might guess. Yeah, the preceding each release, there's a developer meeting where anyone is invited. Anyone interested in Arbor or working on Arbor. And next release is planned very, very shortly. I would say today, but probably early next week. It's been ready for a while, but there are a few tiny bugs that are waiting to be squashed. Then a little bit about building of Arbor. I'm just switching back to the chat. Okay, no questions in the meantime. Feel free to interrupt me at any time if you have questions. Just open your mic because I might not see your chat message in time. But please don't wait with your questions. That's okay. Yeah, Arbor. So how does it work? So it begins with, I've cut out the mathematics from this presentation, but yeah, it begins with the computational model of neurons, which is, neurons can be approximated by an exon delay, synaptic functions, and seen as a set of cables connected in a tree, like the image here on the right, top right shows. This is a model for a neuron, an electric model that can be simulated. These cables are characterized as electrical compartments composed of ion channels, cable, resistance, and capacitance. So yeah, and this can then be represented as a matrix. And this matrix can be solved against current states due to synaptic conductance. And this lets you evolve the system of equations that's behind this representation. And the network spike exchange are represented by concatenation of these matrices. And that's very briefly, without math, what Arbor is doing. This is perhaps not what you're here for. You're probably here for doing some neuroscience, computational neuroscience. So a key element in neuroscience is cells. That's what makes up the brain, nerves. So these are the smallest models that can be simulated in Arbor. The smallest model is one cell and no smaller. That means cells are also the unit of work that's distributed across processes, be that on your CPU, HPC, or GPU. And at the moment, we support cable cells, which are, of course, the main type, the thing you'll come to Arbor for. But we also have an abstract integrating fire cell. There are requests for other cells. We're not quite sure how I mean, that's not what Arbor is good at, but on the other hand, one way of doing research is to have one or a few detailed cells in a larger network of abstract cells. So that's something that we're working on supporting better. But at the moment, there's just the leaky integrated fire cell. You can, of course, make your own single compartment cells with a mechanism of your choosing. So you can pretty much approximate any arbitrary artificial neuron as well. Then there are spiking cells, which are just there to generate some spikes. And we have benchmark cells, which are not really interesting unless you're seeing how fast Arbor can be. So besides the cells, the recipe is the most important neuroscience concept in Arbor, because the recipe describes your model in a cell-oriented manner, and it helps Arbor do things like map global cell ID to cell type, describe cells, and list connections from other cells that terminate on the cell. So Arbor will ask your recipe, which is a class that you define, but you should implement a few functions for it to work that Arbor expects. But it will ask, for instance, cable cell 123, what is your morphology? That's the kind of thing your recipe defines. Or cable cell 123, what's incoming here? What other cells come in on you, are connected through gap junction or synapse? The design of the recipe is an advantage for the parallel instantiation of cell data, because yeah, like perhaps you understand from what I just said, you can break up these kinds of questions, right? So cells can live on different places, and the recipe can still work. Yeah, then how does Arbor translate this into execution? We have the cell group concept. That was the cell group represents a collection of cells of the same type with an implementation of their simulation. That sounds abstract, but it just means there's code that says for a given cell type how to simulate them. And this code can be specific to GPU or CPU or another accelerator. That is up to you, and maybe you have performance sensitive simulation where you think you can write a better implementation, then you can do so. Now, the partitioning of into cell groups of cells is provided by decomposition. It's also something that you can configure or not. You can also let Arbor handle it. And then a simulation in Arbor speed manages the instantiation of model and scheduling of spike exchange and the integration for each cell group. Of course, part of cells are mechanisms. You will probably assign a few to certain regions or the whole morphology. These are, yeah, let's say, usually separate little bits of program. Yeah, and these can be executed in parallel, and they can be implemented in any language, basically. We have the mechanism ABI, but it stands for Application Binary Interface, which means you can write code, and as long as in any language, and as long as it exposes the right ABI to Arbor, it can be used to simulate your mechanism. Included in Arbor is also modCC, which compiles a subset of NModel to optimize C++. So if you use Neuron, you probably use NModel to model your mechanisms. So to a large extent, you will be able to reuse that in Arbor. Now, yeah, the design philosophy of Arbor is to make things swappable by having internal APIs over which components hang together. So like I said here on the top right, cell simulation, you might have a particular faster GPU implementation. Maybe that's a project of yours or a student of yours. You could swap that in as long as you stick to these APIs. And this is, yeah, we think flexible for people who want to change certain bits in Arbor. And I guess it's also very good for us because it makes it easy to understand Arbor. Then I have a quick look at the chat. No questions. Okay. See how many we are. Okay. Yeah, then there's 3 words I want to mention. And they're not specifically about Arbor, but we do facilitate this interoperability, portability, and extensibility. So as a computational neuroscientist, you write code, but often you're not exactly a software developer. So this means you are not always used to writing things in interoperable, portable, extensible ways, which is you just reuse bits that your lab has designed. You reuse bits from neural tutorials, maybe. So it's a topic that Arbor has an opinion about. So this separation of science from execution means that the probability of abstractions, let's say, I should say implementation details of the simulator should not leak into the scientific description that you're writing. Your scientific experiment should not be changed or work around the particulars of a certain tool. It should be the other way around. So this is translates to, for instance, the benefit that you can run your experiment on all kinds of hardware without changing the scientific description. So this is something we take quite great pains to facilitate. Like I said, Arbor is a library, so it means it's interoperable with other tools in your way of working, unlike some other tools and simulators, and portable. So once you have your description, you can take it with you. You can share it, and you don't have to have your colleagues first understand why certain particulars of the simulator are leaking through into the science description. No, it's just not there. So these are things we care greatly about, and we hope you too. What's new? So it's not exactly new version 0.7, but I want to quickly mention what the main new features were anyway. That's ionic diffusion along the morphology, LFI kit integration. We've greatly expanded developer documentation, mainly for ourselves at this point, I guess, but nonetheless. We have an Ellen database tutorial where we extract a model from the Ellen Institute's database, got the exact name, and we show how we, with very little effort, port it to run in Arbor. It is obviously a neuron cell that we extract there. We support homogeneous parameters and stochastic differential equations, i.e. noise. In the next release, we will be able to show single parameter optimization through BluePyOpt integration. So if you do optimization, then there's a good chance you've used or at least heard of BluePyOpt. Now, very soon you'll be able to use Arbor as a target and a backend for that as well. Let's see, stochastic differential equations twice. I guess I made a copy-paste error there. Because, yeah, I think it is merged after 0.7, so it should be here. We have the beginning of structural plasticity. So concretely, you can change the network now during the simulation to a certain extent. We have, I see another copy paste error in homogeneous parameters. Of that, I'm pretty sure it's already in. Sorry about that. Actual diffusion approach for linear integrated fire cells. Okay, now how do you use Arbor? Arbor is written in C++, which I think I already mentioned. But we have a first-class Python API support, so there's nothing you cannot do in Python either. And this is also what we'll see in a moment. We're going to use the Python API. But yeah, should you choose so, you can also use C++. Very few scientists do these days, but it's possible. Yeah, the mechanisms can be written in any language, but yeah, we support the Arbor and model dialect in, how should I say that? That's the most common thing that we also use. Format. And then morphology, file format support is SWC, NeuroLucida, NeuroML, like I said. So the morphology is already first class, and our own Arbor cable cell format. We have the GUI for single cell exploration, and what we call decoration, so the placement of things on the surface of the morphology. Excuse me. And yeah, network design and storage formats, that's an open question. We currently ask you to write a Python function, for instance, that tells Arbor how to, which cells are connected to which. This is very flexible because you can write any Python function there for any network, but it's tied to our API, so that's not, we're breaking one of our own goals. So how to support that well? Of course, the NeuroML CC is one of those ways. We plan to support other ways of simulator independent storage of that part of your experiment. Okay, then I would like to share our website, arbor-sim.org. Documentation is docs.arbor-sim.org, and yeah, you through the website you can find our GitHub and Gitter, and yeah, we are a project that started as part of the Human Brain Project. So hereby acknowledge that. Is there any question from the room at this point? Okay, I see one in the chat from Pedro. Thank you for the question. You were asking about improvements with respect to core neuron and core neuron. I don't know what you mean with stochastic ODE. So yes, we support them. I would say the main improvement is in the performance. So our own benchmarks show that it is, of course, very model dependent what exactly the speed up is that you can expect. But we see that without any effort, we usually get about a factor of 10 speed up, and in certain cases a lot more. Like if we use our GPU, we can reach up to 10,000 times more performance compared to neuron. Core neuron GPU support is relatively new, so we've never tested that. Something we'd like to do, but core neuron is quite tricky to get installed and use, so we haven't gotten around to that. So in terms of features, neuron is definitely ahead of Arbor, but yeah, we think we have the only simulator that can reasonably be used for large networks, and with large we mean millions of cells or more. That's something that's quite difficult to do with core neural, and even more difficult with neuron. So that would be the single most important improvement. I hope that's a good answer to your question.
Yes, thank you. But just what do you mean by features? You said that neuron is a bit ahead.
Yeah, so neuron has about 40 years of building in features, cells, functionality that we don't have. So yeah, that's it. The reverse, I must say, is also true. So in terms of the mechanisms, neuron supports more. On the other hand, the choice to support less is intentional because we don't let you write slow mechanisms in Arbor. So that's something it's very easy to do, and that's actually one of the biggest points for improvement anyone that comes to us has. If they take another look at their mechanisms, their mod files, we almost always find that there are very obvious performance impairing code in them, and that with a little bit of rethinking, also neuron becomes faster, but then of course Arbor is even faster. So usually this is a good exercise if performance is an issue for you.
Thank you. From my side, I can tell you that I have tried stochastic synapses, and that's pretty complex. It takes a lot of time.
For sure. Yeah. Okay.
Thank you.
Thank you for the question. Is there anyone else with a question?
And maybe connected to the previous question, yeah, because you said that with Arbor you can also simulate networks of neurons, and compared to other simulators, for example, as Nest or Pine, since I haven't already practiced with this kind of simulator, so I don't have an idea on how to compare them, but how would you suggest maybe choosing Arbor instead of other kind of simulators for neural networks?
Yeah, so I guess the first question is always, do you need morphological detail?
Okay.
Because if you don't, then Nest is an option. I think there is someone who works on Nest here, but so maybe I'm saying the wrong thing. But Nest, I mean, the simulation of point neurons and morphologically detailed neurons, that's of course two entirely very different things. So depending on whether or not you need that, that will impact the choice for your simulator.
Okay.
So I don't know if you need.
Yeah, well, in my case, I would also consider to have morphological details. So I would opt for something that my idea and the project that I would like to develop, I would consider even those kind of resolution.
Yeah.
So okay.
Yeah, in that case, Arbor becomes an option. Neuron as well, of course. Yeah, exactly. I was thinking of Dennis too. Maybe Dennis can say a little bit in a moment about Nest, but yeah, point neurons is of course the main strength of Nest.
Okay, thank you.
So we're writing a grant with a group of people that want to study plasticity in the context of Parkinson's, and yeah, what's really difficult with other tools. And of course, we're going to have to develop some things in Arbor to support that research. But what's really difficult is really large networks for a long time. So I don't know what's a large network to you.
Well, I already have to assess the actual number, but it may be as first step, maybe 1,000 neurons, or maybe so in the order of maybe some thousand of neurons. But well, obviously.
Yeah. So of course, this question you get a different answer based on if people use point neurons or morphologically detailed neurons in their research. But most people in the morphological world, indeed, 1,000, 10,000 is already large, while of course in the biological world, that's absolutely not large. So Arbor our goal is to help, to help out here and let you simulate networks, groups of cells, structures of the brain that are actually much closer in terms of their biological size than is currently possible with neuron or core neuron. Of course, core neuron is doing their best to facilitate that using neuron descriptions, but yeah. Like I said, another thing is time. How much time do you want to simulate in this project?
Well, it will be something comparable to what he has done. As at the first, something that is comparable is, I'm sorry. I meant I don't have a precise idea, but the main data that I would use are electrophysiological data, so it wouldn't be a very long time, maybe in the order of some seconds, maybe at least maybe.
Yeah,
I would say a minute, but
even
though I know that to simulate even this apparently short period of time, it will require a certain amount of computation. So I know that it's not so easy, even if it is a minute of activity.
Right. Yeah. So indeed, that sounds quite typical. So minutes, according to some people, is already long term, but of course, in reality, that is not long term. Plasticity in a disease like Parkinson's, well, in particular, we plan to study a protocol that treats it, and there we are interested in time scales of hours, and of course, much longer if we could. So this is a challenge, right, in the field of computational neuroscience. We cannot simulate years of whole brain or significant parts of it, and Arbor is an attempt to work towards that goal. And I think if that is something you're interested in, I don't think there's any other choice but Arbor.
Okay. Well, thank you very much for the explanation.
If you're thinking of using Arbor or doing research with it, please get in touch with us. We're very happy to hear your particular use case and help you out where we can.
Okay. Oh, of course. As soon I maybe define more, I define better the idea that I have in mind. I contact you.
Sure. Thanks. Looking forward to that. Are there more questions from the audience? I guess not. Well, then we should get going with a demonstration. I see that in the background I'm still not connected. This is unfortunate. Let me try again. Who here is connected to the lab? Did anyone set this up already? That is not me. Okay. So the idea is that we, of course, this can be done on your local machine as well. You would need to install Arbor for that. But first, copy that terribly long link in the chat. If you are on the eBrains lab, you could type this in. Okay. Let me do that. I am now in. Maybe I can switch the view here. Yeah, I just wanted to say, if you are, so everybody here has eBrains access, right? Who here?
Yes. Yes.
Yeah. Okay. So did you make it into the lab already?
Well, when I try to enter, it opens me the notebook of the previous session. But
okay. That doesn't.
Brent, are you able to access your collab?
Yeah. Well, I don't have.
And open the lab via the collab?
I have it open now through lab.ebrains.eu.
Okay.
So that is good news. But yeah, of course, it's more important that other people also get there. So the easiest thing to do is, if you're in, that you paste this horrible long line and press enter. In that case, you download my network ring demonstration, and it should appear on the left-hand side, and then you can open it. Nicolo, maybe you can let me know if that works out for you.
yeah, I'm trying to insert it in a previous notebook.
Okay.
But it doesn't. Well, maybe I restart the.
Okay. So I hope you can see my lab now. Is that correct?
Yes.
Okay. So what I did is what I said. I entered this line in a blank notebook, and that downloaded the file for me, and I have it opened here. And then it's important to choose on the top right the right kernel. That's the experimental release. That's the version of eBrains that comes with Arbor 0.7. Is anyone following this with me?
Yes, I am following.
Okay, so you made this file. You have it open as like I have here.
I open it locally, not inside my lab space, but
yeah, sure,
I'm looking
of
at
course.
the content of the notebook. Yes.
Of course, for people that want to follow along locally, that's also very fine. In that case, you need to pip install a few packages. I don't know if it's readable. I think it is. So the packages that I use here are obviously Arbor and then Pandas and Seaborn for the plotting. So if you don't have them installed, then you should install them first. Okay. Does anyone need help with this at this moment?
Well, I can't make it work, but I follow I can follow your notebook.
Okay. Yeah, you can execute the line also on your local machine, and then at a later time look at the notebook if you want.
Oh, okay.
That is also an option. Yeah, so in this notebook, everything is prepared, so you don't need to write any code. I'll just guide you through to give you a taste of how it is to work with Arbor. Please interrupt at any time if you have questions. And yeah, I'll get started. Let me execute everything here. So yeah, well, first of all, you should set yourself up with Arbor. If you do so, then you can import the packages. In this case, I use Arbor Pandas Seaborn. I'll use the square root function, and for plotting in the lab, you have to use this incantation, and that's the preface. So, what are we going to do? Build a ring network. I don't know. Yeah, I should scroll here. Okay, it's in this example. Yeah, we're gonna build a ring network, and we'll distribute it over multiple threads or GPUs if available. I will show you if I remember well. Actually, yeah, how that works. The topics we'll cover is to build a basic Arbor cell. Yeah, which will have a sign-up site and a spike generator, and a small recipe that ties these cells together into a network, and then run the simulation and look at some of the results. This is our cell. You can see 4 compartments. 1 is the soma, or in fact 0 is the soma, and the 3 other compartments are the dendrite. It is a morphology, and therefore it is a valid model. It's of course a very toy model cell. How do we create the cell? Now, as a researcher, you probably won't write your own cells quite like this, but it's just here to give you a demonstration that you can. Usually you would get it as a file from a colleague, or maybe you yourself trace it like a SWC file, and you can just open it and you don't have to do any of the following. But if you want to create your own toy cell, this is how you do it. We'll make a function that I hear some chatter there. Okay, I guess someone has the mic open. If you have a question, just speak up. Otherwise, maybe consider muting your mic. Right. The cable cell is composed of 3 components: a morphology, a decor, and labels. This is the Arbor cable cell. Let's start with the morphology. We build a tree of segments, as we've seen here. There are 4 segments, and they are connected in a tree. Let's see. The precise measurements are not very interesting, so I will gloss over them right now. What's important is that these dimensions, of course, are reflected in the numbers that you see here. So this Arbor lets you define each segment with 2 points, X, Y, Z radius. I guess you can understand why that constrains the frustum perfectly. So in this case, it's 12 micron long, yes, and there's a radius of 6, so it goes from -12x to 0 with radius 6 on both ends. And that's it. So we append this structure to the tree, and that would get us the soma shown in red. We can also give it a tag. In the SWC world, the tag 1 signifies soma and 3 dendrite. So you can feel it coming. The second one is the first segment of the dendrite. It has a particular dimension, and it is again composed of a beginning and end point. And what's important is that it is attached to something, namely the previous thing we appended to the tree, which we called S. And then we have, so that's segment 1 here. Then we add segment 2 and 3 in the same manner. I hope you will believe it when I say that this is it. Tag stays the same at 3 because it's still the dendrite, and both are appended to B0, which is what we called the first bit of dendrite here. And that's it. That's how you can create your own segment tree if that is what you need. Like I said, usually you'll get this as a file. You don't have to worry about it. Then you can label things, like I said. Arbor cable cells built up of 3 things: a morphology, a decor, and labels. So those tags, they have numbers, but maybe you want to refer to them with a name, like soma and dent. In that case, you can create a label dictionary and add those names like this. The expression here is an expression in our region and log set DSL. So that's one of the things that some of our users have expressed great joy and interest in, because it lets you, independent of the morphology, define regions. So you can also express things like, give me all distal regions with a radius less than X micron behind this point, for instance. You can express that without having to go in and draw it out yourself. In this case, our expressions are quite simple. Tag 1 is soma, tag 3 is dent. Oh, I skipped a bit ahead. Okay. So what do we have now? We have the morphology and 2 labels. We need a bit more. We need a label for the place where we're gonna connect to other cells. That will be the root and the synapse. Between the cells, we'll connecting them. So from one cell synapse to another cell's root. How do we define those locations? We make a label. One is called synapse site and has this expression. So this expression describes a location at the midpoint of branch 1. And the branch 1 is, in this case, the first dendrite. Rules for how those things are numbered are also on in our documentation, and they are stable, so they will always keep referring to the same location. And the root is a trivial label because there's already an expression in Arbor that describes the root, but we'll add it anyway for ease of use. So at this point, our label dictionary is complete, and the only thing left is a decor. This is the funny name we have made up for describing what is on the cell, on the stage, let's say. So what's on the stage? Let's see. We're going to place a synapse with an exponential decay on the synapse site and give it a label syn. So syn refers to the synapse, no longer, not specifically to the place of the synapse. just the synapse. This is important because we're going to connect to this synapse later on in the network description. Then we place a spike detector at the root. This detector is given the label detector, which is the other endpoint of a connection. You can feel it coming. Then we need some mechanics. So let's see how you write this down. First, we create an arbor decor. Then we put H8 dynamics on the soma and passive properties on the dendrites. That means we're going to paint, because on the region one paints, don't we? So on the soma, we paint the HH density, which is built into arbor, and on the region dent. And in fact, this is just the label, so it could have been anything else. So if you change it up further up later on, you don't have to change this. On the dendrite, they pass density. Yeah, we're going to place the synapse. So this is the where, what, who. We're going to place it on the synapse side. What, the X-pin mechanism, we're going to call it SYN. At the root, spike detector, which clips at -10 millivolts, called, or labeled detector, I should say. And these, this completes the decor, and with this we can create a cell like this. And the function we made, shown here again in full, returns that cell. So we have now a function with which we can make an arbitrary amount of these cells. Voila. That's one part of the simulation. Now the other, the recipe. So let's see how we're gonna do this. Maybe we can just skip to the code right away. Maybe I should stop and see if there are questions, actually. Is there anyone who would like to ask me something about cells? No? I guess I am very clear.
So they have some equivalent to the core in neuron, just to learn, I mean, by relating things.
Sorry, I didn't catch the first part of the question.
Yeah, do you have something equivalent on neuron, like this the core object? What is that actually? What is the main purpose?
Sorry, the purpose of what? Core?
The core. This object that you created here.
So this function, its purpose is to provide a description of a cell, to in fact provide a complete arbor cable cell implementation. That's it.
Okay. Sense.
So this function returns a cable cell based on the 3 labels in the core that we defined above. So by calling this function, you can get instances of this cell. Yeah, that's it. There's not much more to say, I think. Unless you have a specific question. Okay, if not, then I'll move on. So we now can make cells, but now we need to know how they are tied together. So that means we're gonna write the recipe. I think I'll skip over the explanation here. Just go to the code. I think that's the best thing to do. So how one starts is by creating a class that inherits from the arbor recipe class, base class. And on this class, we're gonna implement a few functions that are required, such as number of cells, cell description, cell kind, and connection on, because obviously Arbor needs to know how many cells there are, what kind of cells they are, how they are described, and if there are any connections between them. The rest is optional, but I will go over them anyway. So other than that, this is flexible, and you can do whatever you like in your class, as long as you override those functions or any of the functions, and that they, of course, correspond to what you need, what your experiment needs to do. So the initializer of the class needs to call the initializer of the base class. Then we can call the initializer with the number of cells. So we store it as a value, and then we set the properties to neuron cable properties. So this is a default sort of dictionary that includes default cable properties as they are found in neuron as well. So what you are used to. It can be another set as well. And you can in fact write your own set of properties. But for this example, we'll stick with the built-in. Now then, the number of cells, so the num cells function, this is something that we must implement. It obviously is going to return the variable that we set here, and cells. Now, that's very easy. This next function, cell description, is going to call that function we just created. So in this case, we're going to have a network of identical cells. So the global identifier doesn't actually matter. So it was also not used in the function. So we could even remove it here and upstairs. Doesn't need to be there. In case you have different cells, then of course you would change this function to reflect which cells are which. In this case, all the same. Then the cell kind. So this is shorthand. It lets Arbor know which cell group implementation to use. In this case, they are all cable cells, so we always return cell kind cable. This is also used in partitioning the simulation, which is a detail you don't need to care about, but it is one of the bits of magic that Arbor does to use your hardware as optimally as possible. Now then the network, of course, so connections on. So for a given GID, Arbor needs to know what connects here on this cell. Now, how we're going to configure the cells is that we're going to have one incoming connection from the previous cell. So, and then in a ring, so we wrap around here. So you can see source. So if we are on cell 2, then the previous cell is 1. We of course have to wrap around to make it a ring. And then we return here a list with connections. In this case, just one that connects from the source cell. And of course, we need to say where on the source cell. Well, that's detector. And it connects here on the synapse of this cell with a certain weight and delay. And these are chosen basically randomly. So this is all that defines the ring network, in fact. So you can see this is flexible. Then we need to kickstart events here. So on the first cell, we're going to attach a generator. How we're going to do that is by overriding the event generators method. If we're on the first cell, then a schedule of 1. So we're going to kick off the chain with one event at 1 millisecond of weight 0.1. and then this function returns a list of generators, in this case, one generator located at the synapse with the above weight and schedule. So you can also have all kinds of, we have a Poisson schedule too, for instance. But you can also like we do here, explicitly give timestamps on which there should be events generated. On all other cells, we return an empty list. And it is also nice if we can have a picture at the end. So we'll place a probe at the root of each cell. We override the probes method. I should say implement the probes method. And we return, again, a list, because it can be an arbitrary number. And in this case, a single cable probe. A membrane voltage probe on a cable cell located at root. And then for the property dictionary, we return the properties. That's it. So this describes all of the science of this experiment. It's obviously a toy experiment, but I hope you can see how we create a network, a ring network of a particular cell, and we have connected them, and we kick it off with a single event at the first cell. Okay, let's choose the number 4 for the number of cells and create the recipe. Now we can think about how to execute it. And in fact, we don't have to think about it at all if we don't want. So in this case,
sorry, I have a question, small one.
Yeah, sure.
Short one. What about detecting like a threshold, no, for the transmission of the spike events? Don't you need this here? Because I see that the generator that you define was just to like a one spike.
Yeah.
You don't check if you don't have any threshold checkout before, no, ahead.
Sorry, I don't have any what before?
Yeah, again, as in neuron, you have when you define the connection between two neurons or between a neuron and the synapse, you have to define the wait, the delay, and some threshold for the communication between both the presynaptic and the postsynaptic object. So, are you doing this, or you don't need it?
Yeah, we are doing that. So that's in the connections on function. We have a wait and delay here. I hope you can see that.
Yes, but for the threshold, don't you need to fix the threshold?
The threshold was set earlier in the decor. So we put the spike detector where the event is emitted. And here we have placed the threshold. So it is a property of the cell, not the network, that it spikes at that voltage. So that's why it is here. Of course, you could have different cells with different thresholds. In that case, you could modify this function. But the threshold is located here. Is that clear?
Yes. Okay, sense.
Okay, good. Any other questions before I go on? I see a hand up. Pedro. I guess you had your question just now. Anyone else? Question? Okay. If not, then I go on. So Arbor gives you a lot of flexibility to tune the execution. That doesn't mean that you have to, but it's perhaps good to know that you can. And let's say you want to run on a supercomputer with GPUs on each node. This is something you can explain to Arbor and tell it to use it. And maybe you have written your own cell group that works particularly well on GPUs, then you would like to instruct Arbor to use it. That's all possible here. We won't do anything special right now, but I just want to mention that yeah, you can, and that it works roughly as follows. You first write, you can tell Arbor how to, I see, I modified this a little bit, I see. In any case, before you create the simulation object, you can define a hardware context. That's done with the context class. And here you can tell Arbor what your hardware looks like, what the hardware Arbor should use is. Now, in this case, it is very simple what I'm telling Arbor. It passes a string avail threads. That means use all the locally available threads. What that means, we are now in the eBrains lab, where I believe we have access to 2 CPU cores. So this command will tell Arbor to use 2 threads located on each of those cores. Since we have 4 cells, Arbor will be running 2 cells on each core. You can get very detailed in how Arbor should do this, but if you don't want to, you don't have to. I could also comment this out and just tell Arbor make the simulation out of the recipe, and you figure out what to do. That's also possible. But I just want to give a taste of how you can that you can configure the execution and how a little bit. Yeah. Okay. So of course, in the documentations they go into all of that detail, which I will skip now. For now, we'll stick to avail threads, which means all of locally available cores will be CPU cores will be used, which is usually for a toy demonstration like this a good idea. Now, then we create the simulation object. This is, let's say, the beginning of the simulation. No, it isn't, because first we need to do a few things more. That is to tell Arbor that all spike recorders should actually record. By default, we've turned that off because spike recorders turning them on means that timestamps are going to be stored. And if you have, let's say, 10 million cells, you're going to run out of memory very quickly if each cell has, let's say, 20, 50 spike recorders. So to protect you from blocking all your colleagues from doing any work for the day, it's off by default. But since this is a very tiny network, we can turn everything on. Then we need to extract, well, we added a voltage probe. We would like to look at those traces later on. We need to create a handle to them. Again, this is a bit, sounds a bit convoluted, but again, this is because of how Arbor is designed. It will dispatch cells to various locations in the hardware context that you defined. And of course, it's not going to copy all of that data to a main thread all the time, because that would cost a lot of performance. But does mean we need to store handles to wherever the cells end up. So that's what we do here. Also, we need to set a sampling rate for how often we want to extract them, how often we want to sample. So basically, we create a list of samplers, and the sampler is this thing here. Let's see, where does it terminate? So this is list comprehension. So for every cell, we're going to add something to the list. What is that we add? It affects the handle returned by the sampler, and it points to a particular cell, namely GID. That's the list comprehension here. And then the 0th probe because we have only one. It's the first. On a particular schedule, namely a regular schedule of 0.1, that's 10 samples every millisecond. That's it. This creates a set of handles that we can read out later. Okay, now we're all set. Let's run for 100 milliseconds and see what happens. Yeah, maybe before I move on again, a moment to look if anyone has a question. No, I don't see or hear anything. Then I will move on. Let's again just go to the code. The simulation is run. At that point, under the spikes method, spike times are available, so we can print them. Here is the output. What we see here is a tuple of location and spike time. So this GID and probe index. So you can see that in increasing time, how should I say that? Time. You can see that spiking moves around the network. 1, 2, 3, 0, 1, 2, 3, 1, 0, 1, 2, 3. So you can see that cells are spiking in succession around the network. So that's a good sign because that's what we wanted, right? Let's plot the voltage traces. Like I said, we're gonna need the handles, and we're gonna pass them to the sample method to extract the samples from wherever Arbor executes them. Well, then we do a bit of Panda Seaborn magic to get some nice plot that you can figure out on your own time. This is what the plot looks like. So for each cell in each of the 4 colors, we see the voltage trace at the root. Now, yeah, we begin with cell 0. That makes sense because that's where we kick off the chain, and it spikes. Well, they spike in succession. I think you can believe me that this is indeed what we were trying to build, a ring network where the signal travels around. That is all. Any more questions?